holding the world in your hands. Maybe I could be like, I think it's the Greek god Atlas, right? Putting it on your shoulders. So this is where we look at G on other planets. We know what G is for Earth, and we did calculate it for our natural satellite, the Moon. But what about other planets? Well, here you can see Mars. Right? Mars is the red planet, a very famous planet that we have, and it's one that we're going to be looking at going to Mars in the not too distant future with the Mars 1 mission. And so let's calculate what it would be on Mars. What would the acceleration due to gravity or the gravitational field strength be that on Mars? Well, remember, to do that, we need some details. We need to know, well, since Mars is there, let's just write some things underneath it. So we can say that its mass. Alright, so there's some details there for Mars. I might just put Mars and Earth up next to each other because it's good to get a size comparison between the two, and you can see the two there. So let's just do some calculations and see how it pans out. So we know that the G on, whoops, not the Earth, Mars, is equal to the universal gravitation constant times m over r squared. So we have 6. And we put the mass of Mars in there. Alright, so we can see that Mars has a significantly less, a third less acceleration due to gravity than what we have on the Earth here. Okay? Alright, so that's the acceleration due to gravity on Mars. Let's see if we can do a question to do with Mercury. Alright, so let's rub this off and we'll be back in a tick. Alright, well, let's have a look at Mercury here. Okay, Mercury and Earth. We've got a 2 kilogram brick. Now remember, that's the amount of mass in the object. Right, so we have a brick and it's 2 kilograms in terms of its mass. What does it weigh? Well, remember that weight, well, that's a strange way of doing a W, but anyway, is equal to mg. So if we want to work out the weight on Earth, then the mass is 2 kilograms. The strength of the gravitational field constant on Earth is 9.8, and that's newtons per kilogram. So the kilograms cancel out. Well, what about on Mercury? Well, it's still mg, so it's still got the same mass no matter where you are. But of course the value for G now is 3.6. And because the gravitational field strength is so much less compared to Earth, we have a less weight, 7.2 newtons. Right, just to make it clear here, we started off with meters per second squared, and in my equation here, I put in newtons per kilogram so the units would cancel out. So we had newtons. Well, they're exactly the same thing. So remember that newtons per kilogram is the same way as writing meters per second squared. Now, how can I prove that to you? Well, a newton is the same as writing kilograms per meters per second squared. Right? If you remember that F equals ma, mass is in kilograms, and acceleration is in meters per second squared. And usually when we talk about the force, we say, oh, the answer is in newtons. So really that is the same as a newton, right? The newton, by definition, is the force required to move 1 kilogram and accelerate that by 1 meter per second squared. So if that newton is equal to that, and then we've got the kilogram here, they cancel and we end up with the same. Okay, so even though the question gave us meters per second squared, we can write newtons per kilogram, and then we end up with our final weight in newtons. All right, hope that makes sense for you. Let's do another question. Let's just check the crib notes. Okay, let's do Jupiter. All right, let's do Jupiter. Now, Jupiter is a very amazing planet. It's a gas giant, and it has, like, I think I think 67 moons, something like that. So it is an absolute phenomenon in terms of a planet. So here we can see Jupiter, and I'll just put Earth near it as well so you can see a size comparison. And the red spot is a storm that's been going for, you know, I think I read somewhere maybe 300 years or so, but it's the size of 2 Earths, so it's pretty incredible. So let's see what G is on that planet. So here we have G for Jupiter, G and then J for Jupiter, and we put this into the equation like so. Now, I don't have my calculator right here at this very second. Now, this is the value that I've got written down in the book here, which I think I got from research. But when you actually put these values in, I think you get closer to 25. But anyway, it's pretty close to, if I was to round it off to 2 significant figures, it would be 25 anyway. So, quite a significant, you know, acceleration due to gravity on Jupiter, 24.79 meters per second, or 25. So that's it for this video. Hope that makes sense. We looked at how to calculate G on different planets by using this formula here. And you know, sometimes in questions they ask you to do a ratio of the G for different planets. So you can set the equation up here and do a ratio and work out, you know, Earth is 2 times more than this planet or whatever it might be. So hopefully that makes sense to you. Catch you in the next video where we start to actually look at planetary motion, satellites, the idea of Newton coming forth and talking about how we have orbits that circle the Earth in terms of orbital velocities, etc. See you in those videos.